The last video was an introduction to the concept of energy and how energy is related to a scalar quantity called work. And in that video, I said that you can think of energy. Energy is very nebulous. It's hard to define in a succinct fashion. But think of work. You know, work is by definition in a physics textbook a mathematical equation that is a dot product between force and displacement. Two vectors. You take the dot product, the scalar product between them, and you get the scalar quantity. So in the textbook, you might see that work is force applied over some distance. But I don't find that definition very useful conceptually. For me, when I think of work, what I'm thinking about is that when work is done, first it's done by a force. So forces mediate work. And what's happening is energy is changing forms, or energy is moving from one object to another. So work is what's done, and it's all mediated by forces. So forces mediate these interactions, and work is energy changing forms or flowing from one place to another in the world around us. So here's a summary of the stuff, all the stuff that we talked about in the last video. Work is the dot product between force and displacement. The total work done on an object is equal to the net force dotted into displacement, and it turns out that's equal to the change in kinetic energy, or the energy of motion of an object, and where kinetic energy is defined as 1/2 m times v squared, where here v is just speed, not velocity. So again, you know, what we're dealing with here are scalar quantities, and this will actually facilitate the study, the analysis of a whole bunch of problems which would be really, really complicated if we tried to analyze them simply using kinematic equations of motion and Newton's second law, which of course involves vector quantities like acceleration, force, and velocity. Okay, so by switching to a scalar quantity, we can study more complicated situations, such as a roller coaster where a car is traveling along a curved path. But we lose some information as well. We lose some information about the direction of the physical quantities. So in this video, we're going to talk about a different type of energy called potential energy. So if kinetic energy is the energy of motion, potential energy is the energy an object has by virtue of its position. So we're going to talk first about the energy a mass has by virtue of its height above the surface of the earth or the floor, and this is called gravitational potential energy. So if I elevate a mass, if I take a mass and elevate it, the act of lifting that mass gives it potential energy, gravitational potential energy. And if I were to then drop that mass, that potential energy becomes kinetic energy. As the mass falls, the potential energy is converted to kinetic energy. So this is an example of, you know, as the mass is falling, there's energy conversion happening. The energy stays with the object. Conversion. The energy stays with the object, but as it falls, its potential energy is converted into kinetic energy. And so this is happening because there's a force doing work, and that work results in this energy conversion. And in this case, the force doing work is gravity. The gravitational force is driving this conversion from potential energy to kinetic energy. In the same regard, if you elevate a mass, the force of gravity is mediating the conversion of the energy it takes to lift a mass into potential energy. Okay, so let's take a look at the work done by the force of gravity, and we'll show that that's equal to the change in potential energy that the object experiences. So first, we're going to use the symbol U to represent potential energy. In textbooks, you'll sometimes see PE for potential energy, but you also see U. We're going to stick with U. And for the time being, we're going to focus on potential energy due to gravity. So I'll make that U sub g. So if I have a mass m and I lift it some distance d, or some displacement d, straight up, the force of gravity is pulling straight down. And we can write that as, instead of using W here, I'll use F sub g, because W is going to be used for work. And the weight of an object, or the force of gravity near the Earth's surface, is just its mass times g, the acceleration due to gravity. So the work done by gravity is going to be Fg dotted into d, the displacement, where here, because the displacement is up and the force is down, the dot product is cosine of 180 degrees, which is -1. So we end up seeing that here, when the mass is rising, of course cosine of 180 is -1, right? So we end up with negative work done by the force of gravity, or negative mg d. And I said earlier that what's happening as you elevate a mass is you're giving it potential energy, gravitational potential energy. So as the mass rises, the gravitational potential energy is increasing. So the change in potential energy is greater than 0. So how do we reconcile the fact that the work done by the force of gravity, the thing that is causing this energy to be stored on the mass as it rises, and the change in potential energy have opposite signs? Well, that's easy. You set them equal to one another, but you include a negative sign, like so. So the change in gravitational potential energy is equal to the negative of the work done by gravity, which is equal to mg times d. So this suggests a way that we can write a formula for the gravitational potential energy of an object as a function of its y position, how high it is. So we think about this mass moving upward from some initial y position, y1, to some final y position, y2. If we write the gravitational potential energy at these 2 points as mgy, then the change in gravitational potential energy from y1 to y2 is mg delta y. And the delta y here is equivalent to the d, or displacement, from the previous slide. All right, so let me point out something that's interesting here. Your choice of y1 and y2, what the actual values are for y position 1 and y position 2, depends on your y equals 0 point. If I use a y equals 0 point of down here, then both y1 and y2 are positive. But if my y equals 0 point is between y1 and y2, then y1 is negative and y2 is positive. So y1, the actual value of y1, and the actual value of y2 is relative to whatever you say is your y equals 0 point. Therefore, the actual value of u at point 1 and point 2 is also it also depends on what you call your y equals 0 point. So they're relative to y equals 0. So in absolute terms, potential energies used, the numerical values, don't really have much use to us because they depend on your y equals 0 point. But as we'll see, for most practical situations, what really matters is not u, but how u changes when you go from one place to another. For example, in the previous slide, we saw that the work done by gravity is equal to the negative change in gravitational potential energy. The negative change in gravitational potential energy. So let's consider what happens when a mass falls. As it falls, the work done by gravity is going to be positive because the force points down and the displacement points down. But the change in gravitational potential energy will be negative because its potential energy is being converted into kinetic energy as it falls. But just like before, we can write that the change in gravitational potential energy is equal to the negative weight times displacement, like this. Or in other words, change in u equals the negative work done by gravity. So it turns out that, as later we'll encounter other forces that are like gravity, where, gravitational force is special in this case because the gravitational force acting on an object causes energy to be stored or released from the object. This is associated, in other words, the force of gravity is associated with a potential energy. And we'll see other forces like the spring force or elastic force, which also has this property. There's a potential energy associated with it. And for all of these special forces, which are called conservative forces, more about that in a minute, for all of these forces, the work done by these forces is equal to the negative of the change in potential energy that the object experiences. So gravity is a conservative force, but in general, we'll encounter others. When a conservative force does work, the negative of that work is equal to the change in potential energy experienced by the object on which the work is being done. So this is a general expression, not just for gravity, but any time a conservative force is doing work on an object. So let's talk about why it's called a conservative force, okay? And this begins with defining a concept called mechanical energy. So we'll define the mechanical energy of an object as the sum total of that object's kinetic energy and that object's potential energy. And we'll designate this E. E equals K plus U. All right. Next, let's break up the total work done on an object into two parts. The work done by conservative forces, which for the time being is only gravity, that's the only one we've considered, and the work done by everything else. There's only a few conservative forces. All other forces, such as tension and friction and pushes and pulls, are non-conservative forces. All right, so the total work equals the work done by conservative forces plus the work done by non-conservative forces. And we previously saw that the kinetic energy that an object has is equal to, wait, let me hold on. I missed a step. Okay. So if the energy of an object the mechanical energy is the sum of its kinetic and potential, then when studying an object and how it moves or changes or goes from one place to another in space or time, the change in mechanical energy is equal to the change in kinetic energy plus the change in potential energy. And we previously saw that change in kinetic energy equals the total or net work done on an object, and the change in potential energy is equal to the negative of the work done by conservative forces. If you put this all together, over here you see that the change in mechanical energy equals the total work minus just the work done by conservative forces. And of course, the total work minus WC is WNC, the work done by non-conservative forces. So change in mechanical energy equals work done by non-conservative forces. And so now we're ready to talk about what being non-conservative really means. Okay, so for any situation, an object like a roller coaster, moving from one point in space and time to another point in space and time, the change in mechanical energy that the object experiences is going to equal the work done by non-conservative forces. So let's consider the situation of a roller coaster, this roller coaster rolling down the hill. Well, one thing we know is that in the real world, the forces acting on the roller coaster are the force of gravity, there's a normal force, there's a frictional force, there's probably air drag, there's lots of forces. But the force of gravity, well, the normal force is always going to act perpendicularly to its displacement, so it's not going to do any work. The frictional forces, in many situations, we might be able to ignore because their contributions to what's going on may be small. I mean, it's reasonable that roller coasters are designed to use low friction components in their wheels and in the track so that they roll better. Okay, so if we ignore everything except for gravity, gravity is a conservative force. So it the only force doing work is a conservative force, the work done by non-conservative forces is going to be equal to 0. So if friction is negligible, we can say the work done by non-conservative forces is equal to 0, in which case the change in mechanical energy of the roller coaster as it rolls down the hill is equal to 0. And the change in mechanical energy is change in kinetic plus change in potential, which is equal to the kinetic at the bottom of the hill minus the kinetic at the top of the hill plus the potential at the bottom of the hill minus the potential at the top of the hill, and that equals 0. And of course, delta E equals E2 minus E1. So if we rearrange this, what we see is when the work done by non-conservative forces is equal to 0, delta E is equal to 0, which means the mechanical energy of the roller coaster at the top of the hill is equal to the mechanical energy of the roller coaster at the bottom of the hill, which means mechanical energy is conserved, which means it doesn't change. So when only conservative forces, in this case gravity, do work, when there are no non-conservative forces like friction doing work, mechanical energy is conserved. The total mechanical energy at the top equals the total mechanical energy at the bottom of the hill, which means the sum of K1 and U1 equals the sum of K2 plus U2. If we expand this out, we find that we have a very powerful problem-solving tool. 1/2 mv1 squared, which is K1, plus mgy1, which is U1, equals 1/2 mv2 squared, which is K2, plus mgy2, which is U2. So if we know the height of the hill and the height of the car when it gets to the bottom of the hill, we know the velocity of the car at the top of the hill. We could calculate the velocity or the speed of the car at the bottom of the hill using this formula. Another interesting thing that happens here is there's an m in each term. It will cancel. So the mass of the object doesn't influence the speed at the bottom of the hill. This is pretty important for roller coaster design. You wouldn't want the speed that the roller coaster travels to depend strongly on how many riders are in the roller coaster. If it did, it would behave differently on different days, busy days versus slow days at the amusement park. So what happens when the work done by non-conservative forces is not 0? So what happens in a situation where there's friction and friction does a significant amount of work? Well, in that case, mechanical energy is not conserved. The change in mechanical energy, which is the kinetic energy and the potential energy the object has, is equal to the work done by the non-conservative force. So if you have a car rolling along a surface where there's some friction, a significant amount of friction, the car is going to slow down. Well, the change in mechanical energy, which in this case is a change in kinetic energy, is equal to the work done by friction, which in this case would be negative because friction points this way if the car is moving this way. So the kinetic energy decreases. It slows down. The mechanical energy decreases. Okay, so we'll practice some of these concepts in class. But now we have a very powerful tool. We can study more complicated situations like roller coasters rolling downhill where the track is curved. And by neglecting, by shifting focus from vector quantities like forces, velocities, and accelerations to the scalar quantities of work and energy, we can make a lot of progress. We lose some information, but we gain a lot of power in the types of problems we can study. All right, so one more thing, and that's the concept of power. Power is not equal to energy. What power is power is defined as energy per unit time. And power is a measure of how quickly energy is being converted from one form into another or being transferred from one object to another. So an equivalent way of thinking about power is not energy per unit time, but the amount of work done per unit time. And of course, energy and work have equivalent units, joule. So the unit of power would be a joule per second, which is also called a watt. If we rearrange this equation and we solve for E, we see E equals power times time. So the amount of energy utilized in a process or by a device or converted from one form to another in a given amount of time is the power being utilized in that process times how long that is being done for. So 1 unit of energy would be a unit, the SI unit for power, watt, multiplied by the SI unit of time, which is second. So 1 watt second is equal to 1 joule. Well, it turns out that 1 joule or 1 watt second is a very small unit of energy, but one you'll encounter more often is the kilowatt hour. And 1 kilowatt hour, there's 1,000 watts in a kilowatt, and there's 3,600 seconds in an hour. So 1 kilowatt hour is 3,600,000 watt seconds, or 3,600,000 joules. And you'll encounter this unit of energy often when it comes to electricity. This is the amount of energy that you get billed for on your electric bill. Okay.